So I'm going to talk about reinforcement learning. It's a topic I'm really excited about. You'll see a lot of walkthroughs and videos out there that talk about reinforcement learning and always mention a step closer to AI or feels like AI, and it totally does. It feels like there's that extra layer of intelligence that's refreshing to machine learning. I've been at it for a few years, and the way I've always heard machine learning is described as either supervised or unsupervised. And now I'm hearing it recently as supervised, unsupervised, or reinforcement learning. So it really made its way into this duo that's now a trio. The main difference between supervised and unsupervised and reinforcement learning is supervised and unsupervised, you need historical data to model. Reinforcement learning, you don't. It works on a reward system. Imagine is a kind of example we're going to look through Q-learning, where you want to go from point A to a goal point, and you know it does not need to know the map. It'll try every combination until it finds the best way to get from the starting point to your goal point, and that's very powerful in of itself because there is no data. So it's actually kind of searching out there, and it's very interesting. The other difficulty I've seen trying to understand reinforcement learning has been that a lot of the blogs out there are very complex. They either bring in game theory or deep search algorithms. I just wanted a very simple Python example, and that's what I'm going to show you today. And I'm copying most of the code from Mick's blog, which is mentioned in my walkthrough, that finally made it very simple, stripped all the the superlative and kept it to the point. And thank you for that, Mick. And then we'll look at a second example, a little bit more complex, where we bring in a little bit more intelligence to it, which I think is very exciting. But let's first understand what reinforcement learning is all about, and then we'll move forward. Okay, so let's start with the code. Let me just paste it into IPython and then talk about it. So all the code is on the blog. It's mentioned there. Please go there to get the source. We're going to start with a point list. The point list represents your map, all your potential points you can go. Don't worry about going the reverse. Just think about it going one way. We can go from point 0 to 1, 1 to 5, 5 to 6, 5 to 4, 1 to 2, 2 to 3, and 2 to 7. And our goal is point 7. Our starting point is point 0. So let's look at these. 0, 1, 1, 5, 5, 6. And it's mapped out. 0, 1, 5, 6, 5, 4, right? That's exactly so. 0, 1, 1 to 5, 5 to 6, 5 to 4, 1 to 2, 2 to 3, 2 to 7. That's all you have to do when you create your points list. That makes things a lot simpler. And we're going to use NetworkX to visualize it. That's also nice. By describing like this, you can easily visualize your, actually you can do it a few times. It's randomly drawn, so do it till you get a decent picture that you can understand. Okay, this was not too bad. Starting point 0 to 1 and 1 to 2, 2 to 7. That would be the ideal route, right? That's what we want our Q-learning algorithm to figure out on its own, right? We're just going to give it the map and say, hey, you figure it out. Point 3, 6, 5, 4 are noise, and that's going to have to contend with those as being things that don't help it reach its goal. Okay. So we declare the matrix size because we go from 0 to 7. We know our matrix is going to be 8 to 8, and we create a rewards matrix. A reward matrix is just basically a representation of what I just showed you in a form that the Q-learning algorithm can read. So let's not worry too much about it. If you want more details about that, go to either Mick's blog or the other blog I mentioned in the walkthrough that goes through more of the theory. There's 2 blogs mentioned that are really good and simple. So now we're going to take our points list that we created and fill out the values in our rewards matrix. Right now it's all -1. We've just initialized it. And now, as you can see, it's a bit different. Point 0, 1 is here and 1, 0. So the point and its inverse are going to be here. 1, 5 is here and its inverse, right? So 1, 5 is here and 5, 1 is here, right? So it's going to plot, everything where it cannot go is a -1, where it can go and it doesn't reach the reward, it gets a 0. So you have we do, here we're going to go from 0 to 1 and 1 to 0 because you can go both ways. The only ones that are not mapped twice, the reverse is the goal point. So you can go from point 2 to 7 or 7 to 7. It likes to have the loop back. So These are the 2 goal points. Let's look at the map again. You can go from point 2 to 7 to win, or you can go from 7 to 7 to win, right? It needs that for the algorithm, but really we're interested in going from 2 to 7, not from 7 to 7. It's redundant, but it needs it, so we'll leave it. And it creates our reward matrix. Of course, this reward matrix is not shown to the algorithm. The algorithm is only going to use it after the fact to figure out if it made a point or lost a point, right? So this is the reward system. And a quick caveat, they've used reinforcement learning with Atari games where they just see the pixel values on the screen. They don't see the actual game. They don't know if it's asteroid or paddleboard. They just see the pixels on the screen, and they can read the score and move whatever control there is. Maybe it's a paddle that can go left and right, that's all. It knows nothing else. It can move a paddle, read the score, and read each pixel on the screen. And it's going to try every single combination until it sees the score consistently going up, and it knows it's doing well, right? That's kind of the concept here as well. So now we're going to build the brains, and this is very much copied from Mick's blog. So for more details, please go there. But in a nutshell, we give it an initial state. There's a function that's called available action. That's going to return all the potential moves our bot could take, right? For example, if it's at number 1, it can go either 5 or 2, right? So it's going to return 2 potential moves. The sample next action is simply going to take 1 randomly. And the update function, this is kind of the brains of it, including our Q learning function, right? This is the modeling function. Again, go to both of those blogs if you want to get more details. But the one parameter that you can tune is the gamma. That's a parameter, the learning rate that you can tune. Everything else kind of has to be that way. Okay, so now and this update function is basically going to update this Q matrix, which is right here. The Q matrix is kind of it's where the model is going to save how well it's done on its different routes, right? It's going to keep a tally of where it does well, and the biggest numbers eventually are going to become the most efficient route. And this is what it does. This is what this update function is going to constantly figure out where the bot went, and then look at the reward matrix, right? And see, okay, this is where you want to go. This is a score I give you, right? It doesn't really have access to guess the move, to look at the move in the future, right? It can only look at it in the past, but it will get a score based on how well it did. Okay. So moving on. And now we have the training and testing function. So I'm just gonna, let me just do this first. Actually, let's do this in by chunk. So the first thing is the training. It's going to basically loop through what we just showed you 700 times. That's more or less a good mean of values, an average values to get things done. Then it's going to give us a score every time, how well it's doing. And finally, it's going to give us an overall score. So let me run this. And here is the Q matrix, where it has learned the best moves to, the ideal moves to get to where it needs to go. And now we're going to run our testing. And it returns the most efficient passes from 0, 1, 2, 7, right? And if we go back, we indeed see that 0, 1, 2, 7 is exactly where we want to go, right? We want to start from 0, finish at 7. So perfect. It figured it out. And let's see, we can plot also kind of its journey to see how well it did. So right, we had it run 700 times, and it looks like right around 400 or right around this area, right? It converges, meaning that it does find the ideal path, and all the rest, all this is extra. It does not need to do more. But so that's it, really, right? We gave it a map, and we said, go at it, try many combinations, and in around 400 combinations, it figured out what's the easiest route. So what's exciting about Q-learning and reinforcement learning is you may not even have a map, right? You may just know that the goal looks like something like, find, actually we're gonna look at an example next about finding honey. We're gonna say, hey, find a beehive. I don't know the map, but I want you to find a beehive. you could very well tell, every single step, it would figure out where it can go next. Maybe it can go left, right, up, down, right? It could figure out the map on its own. And you don't even, and you as the owner of the reinforcement learning program, you may not know the map, but you can launch your bot, it can figure out where to go, and it will stop once it finds the honey. That you may not know where the honey is, but at least you know you want it to find honey. That's what's really exciting about this approach. It's very different, and you really start seeing that, automated things going out there in the real world looking for things and not stopping till they find them. I mean, it's terrifying, but awesome at the same time. So let's take this example one step further. Hopefully you're still with me, and we're going to add environmental details. So let me look at the artwork that my kids did. Here you have 0.0. So imagine this is a bot, an automated bot looking for honey. He has his jar, and he wants to get to the beehive, right? The assumption here is that there's a factory that makes a lot of smoke, and bees don't like smoke. So we know that if the bot finds smoke, and let's say at 0.5, he could be finding smoke already, he would turn around, right? Or if he saw a bee at 0.2, he would keep going because he knows bees mean a beehive, keep going. So these are environmental factors that I would like to collect as it looks for, as it tries to find his goal of 0.7, right? At this point, it may not know that bees and factories have anything to do with what it's looking for. So the bot needs to do it once, figure out how to get from 0.0 to 0.7, but all along the way, take snapshots of what it sees around it, right? Oh, at 0.5, I found smoke, note smoke. At 0.2, I found bees, note that there are bees, right? And it would catalog these things. So when it comes back, you can then use a more traditional classification model and kind of figure out, are there any environmental factors that help me find my goal? And you'll find out that bees have a positive coefficient for hives, and smoke have a negative coefficient for hives. Thus, the next time it goes out, that bot goes out, it can start thinking about, though I don't really have a map, though this is reinforcement learning and I'm rewarded, I have learned in the past that bees do tend to mean that there's a hive around. Let's keep going. So it's a bit of a crude example that I have, but just to kind of give, that was the wrong piece of code. So we're doing a slightly different map, but something that can explain what we're looking at. So our starting point is still 0.0. Where is it? It's right, start, right, where it says start. And we want to get to bees. We want to get to the beehive. So now we have that hint, right? We don't know yet, but there are bees at 0.2 and there's smoke at 0.4, 5, 6. So any of these, hopefully at 0.5, it can turn around, and bees, it can keep on going, right? So we're going to rerun our Q matrix, basically fill out what it found along the road, the Q learning. But we're going to add a slightly different ability. We're just going to add an extra ability of collecting environmental factors. At this point, did you find bees? Or at this point, did you find smoke, right? So let me just run that. It runs that. And now we return two extra matrices, one where it found bees and one where it found smoke, okay? And then we're going to kind of subtract these matrices. Let me just show you what it looks like so that we kind of give it a bias. And so now the positive are going to be the bees and the negative values are going to be the smoke. Keep in mind that normally you would go out in the field, get your data, and then you do the modeling after the fact. So, okay, what did the bot return on its journey, looking for the most efficient path, and it found these different things that on its path. Let's see if there's any correlation to the goal we're looking for. And here it told us, bees is positive, smoke is negative, and now we can send it back on its journey with this type of map. So here I'm making another assumption, right? We're going to have it do the exact same map as before. Thus, that's why I can give it the same environmental matrix, which is a map of where the bees and the smoke are. But in reality, you would kind of have it go through a completely different map and figure out, there's a bee +1, there's a smoke -1. but that would make just this walkthrough a little bit more complicated, but the concept remains the same. Okay, so I'm going to run the code. And here now, we're going to, as we run our training code, we're going to say, available actions with the environmental help. So it's not only go out, look for all the next potential actions, look at the next potential actions with a positive bias. Thus, this is going to, if it finds smoke, it's going to reject it and not offer it. If it finds bees, it's going to accept it, or if it finds nothing, it's going to accept it. If we can get a slightly better plot. And here, it does seem to want to converge a little bit earlier, right? The other one was around 350. This is definitely around like 253. So not a huge difference, but the point here is not really to worry about my example, whether it makes sense or doesn't make sense. The point here is to see how can you apply this Q learning, which is really, if you imagine it physically as a bot going out there in the real world and kind of, doing its thing forever until it finds its goal. How can you use that to get, additional data, so the next time around you want to, get your goal, you can get there a lot faster. So that's the idea, and I think it's very exciting. And I think in these approaches such as these can be applied to all sorts of things, medicine, financial world, all these things. I think it's fascinating.